Hi! In this video, we're going to present 4 different problems that are increasingly intense about boxes that are attached to other boxes involving a pulley sometimes. We'll start with problem 0, and you'll see why it's problem 0 in just a moment. Your challenge is to find the acceleration of this box. Hey, that's not so bad. There's one force acting on it. And if we apply Newton's second law in the y direction, let's put y that way and x that direction, then we'll say that the net force in the y direction is mass times acceleration in the y direction, and the net force is simply negative m times baby g is equal to m times a sub y, so a sub y is negative baby g. We're finished, yay! Okay, problem number 1. In problem number 1, you've got a mass on a frictionless surface attached via a string to another mass right here. And one intermediate problem is, what the heck is the tension right there? But we're trying to find the acceleration of this mass, and would you agree that this acceleration, this mass's acceleration, will be equal to this mass's acceleration? I hope so. So we're going to need 2 free body diagrams. And here is the first mass right here, and there will be some forces acting on it. First of all, there's m times g acting down, and then there's the normal force acting up. Over here, ooh, let's see, there's a tension pulling that sucker to the right. And then the second mass looks like this. It's a little bit simpler free body diagram. There is m times g pulling that mass downward, and then there's tension pulling it upward. How should I draw tension? Let's think about this very carefully. If tension is equal to the weight of this box, then this box will be in equilibrium, which would mean this box is not accelerating. But that's unreasonable. There's no friction right here. There's nothing to keep this from sliding down. So we know that the tension must not be equal to m times g. A lot of people think it is. You should slap them. The tension is smaller than m times g so that we can have a net force. All right, so let's make Newton's second law in the relevant directions, but we're going to have to set up a coordinate system. I like that also. Let's say the acceleration right here is going to be in the x direction. So over here, we just say the net force in the x direction is equal to mass times acceleration in the x direction. This is actually what we're trying to find, the acceleration in the x direction. And the net force right here is simply the tension. So we've got T is equal to mass times acceleration in the x direction. Put a box around that equation. That's what Newton's second law taught us. In Newton's second law over here, we're going to find that the net force in the y direction is mass times acceleration in the y direction. And, well, that's just, let's see, we've got tension in the positive y direction. And, ooh, you know what we should do? We should take this coordinate system and we should assign it to that problem. And we should make a new coordinate system right here where x is downward. How do you like that? Can we do that? That way then the acceleration will be in the x direction for this one, and the acceleration will be in the positive x direction for this one. It'll be easier for us to connect them. So now I'm interested in the net force in the x direction is the mass times the acceleration in the x direction. And tension will not be positive. mg is positive. And then I'll subtract the tension because it acts upward, which is now the negative x direction. We've got mg minus t is m times a sub x, and I can put this sucker in a box. Look at these 2 equations. We're trying to find acceleration. We'll have to do a substitution. It looks like t is already solved. I'll take it and plug it into right there. My new equation is m times g minus m times a sub x is equal to m times a sub x. Whoa, that's a little bit creepy. What's going to happen here? What do you want to do? I see 2 beautiful things that we could do. You want to cancel out the m's first? Too bad. I don't want to yet. I'm going to say m times g is equal to... Wait, is this just 0? Oh shoot, did we just prove the acceleration of gravity is 0 on Earth? I hope not. Check it out. We're adding this to both sides. It's 2 times m times a sub x. We're trying to find a sub x, so we better divide by 2 times m. I've got m times g over 2 times m is equal to the acceleration in the x direction, y. That's the same thing as baby g over 2. So for some reason, there should be a minus sign here, shouldn't there? Where's that minus sign? mg minus that. Oh, there should not be a minus sign because we set up the acceleration to be in the direction that's downward, so it's a positive number. Okay, this answer right here says that the acceleration of gravity is half what it was in this problem over here. I think that's because there's twice as much mass accelerating, but only the equivalent amount of force downward because of gravity to this problem. Same force downward because of gravity, but twice the mass to accelerate. So the acceleration of the block is halved. Let's do one more. I think we've got time. The third problem in our exciting adventure with boxes on ramps attached to pulleys and ropes and other boxes is an angled ramp and a dangling box. And I'll remind you of our previous problem where we rocked 2 boxes attached to each other by a string. There was a pulley here, and this one was flat with no friction. And we found that because the effective mass had doubled, yet the force of gravity was the same on the system, the force of gravity of just one box was acting on the system, we found that the acceleration was baby g over 2. Twice as much mass, same amount of force, so you get half as much acceleration. That's very reasonable. And we did it in a wonderfully complicated manner that we can use to apply to the next problem also. I'm just hoping this stuff makes sense for you. In this problem, we're expecting there to be even slightly less acceleration because this mass is now feeling a force that's causing it to go opposite the ultimate acceleration of the system. So this will cause the acceleration to be even lower than baby g over 2, and it will probably depend on that angle of 18 degrees that I've put in there. And we'll leave it as a theta, we'll treat it like that. So the first thing that we did was we identified that we need free body diagrams. And let's do that again. We need a free body diagram for this mass. Let's see, it's got the force of gravity, which I'll call m times baby g. It's got a normal force going this direction. And I'll label this as box 1. This is box 1 here, and this is box 2 there. And box 1 also feels tension pulling this direction. There's tension. So let's establish a coordinate system for box 1. Looks like we've got 2 vectors that are normal to each other and one that's not normal. Probably makes sense to put x and y like that. And well, let's go ahead and apply Newton's second law. And before we do this, we should probably resolve this vector, which is not in x or y. That's a right angle right there. This is m times g times, ooh, what's this angle right here? What is it? What is it? What is it? What is it? See, it's 18? See that? Yeah, that must be 18 degrees right there. Okay, so this is 18 degrees, and we'll say this is m times g times, it's the opposite, so it looks like it's the sine of 18 degrees, and this is m times g times the cosine of 18 degrees. And then, well, time for Newton's second law in both directions. The net force in the x direction is mass times acceleration in the x direction, and the net force in the y direction is mass times acceleration in the y direction. Let's see, which way will this box be accelerating? Will it be accelerating in the x direction? And oh, we are actually trying to find the acceleration in the x direction for this box, because this one will accelerate like that, and this one will accelerate like that. So let's see, we'll say this is mass times acceleration in the x direction, then we need all the forces that act in the x direction. So we've got tension going to the right, that's positive in the x direction, and we've got, let's see, gravity acting down and to the left. So we've got minus mg sine of 18 degrees. And we'll box this equation and grab ourselves another one. We're actually not going to need to look in the y direction. It would be useful for finding the normal force, but because we see that there's no friction, it's not necessary to go that direction. So let's go over to box number 2. And in box number 2, we've got, again, a very simple situation where we've got m times g, and upward is the tension. And are we arguing the tension is the same as m times g? If tension is the same as m times g, will this box accelerate? It will not. So tension has to be smaller than m times g in order for this whole system to accelerate. So let us check out what will happen here. We've got net force. Which way do you want to call x? You want to say that the acceleration is in positive x again? In that case, we should call this direction x. I guess we'd have to call that way y, but we're not going to need it. Let's write down the net force in the x direction is mass times acceleration in the x direction. And then we can say mass times acceleration in the x direction. And then the net force is, well, we got m times g. And then we have to subtract t because t acts upward, but m times g acts in our defined x direction right there. Here's our second equation. Again, we have two equations and two unknowns, and we will probably find that the mass will cancel out. That's why I put these guys as the same mass. So let's, since we're trying to solve for a, let's get an equation in terms of t and plug it into the other equation. We could solve this equation in terms of t. T is mass times acceleration in the x direction minus m times baby g times the sine of 18 degrees. And we could take this sucker right here and plug it in right there. And we get m times g minus m times a sub x minus m times g times sine of 18 degrees. Let's see, we're supposed to be subtracting t. So t is this. I'm going to have this term negative, and this term has two negatives, so it's a plus. And that equals m times a sub x. I'm interested in getting a sub x. So I'm going to get everything with a sub x on the right side. Notice also that everything has mass in it, so we can cancel out mass. This term has mass, that term has mass, that term has mass, that term has mass. Mass is canceled out entirely. Okay, and I'm going to add a sub x to both sides, and I will get baby g plus baby g times sine of 18 degrees is equal to 2 times a sub x. We solve this for a sub x. Let's check this out. Solve this for a sub x. We're going to get a sub x equals, and I'm going to factor out a baby g divided by 2 times 1 plus sine of 18 degrees. That makes me a little bit uncomfortable. Let's find out what the sine of 18 degrees is. Sine of 18 degrees. Oh, I must have made a mistake. You see why I don't like this? This means that the acceleration is bigger than it was over here. For this problem, we found it to be baby g over 2. In this one, it's baby g over 2 plus a positive number. Check the minus signs. Where did I make a mistake? Here I said that tension is... this should have been plus right here. Look, as I added this to both sides, that's a plus sign right there. Make sure that you get that in your notes. As I plug it into here, both of these terms should be negative when they're plugged in. So I'll come over here with a blue pen. Both of these should be negative over here. This one should be negative, and this one should be negative. And then this will be a minus sign as we continue on. And this will be a minus sign as we continue on. There, we've got the right answer. I'll write it again because it's nasty. G over 2, 1 minus the sine of 18 degrees is a sub x. So not only Is it less than baby G? It's less than half baby G. Because if I take this thing that's in the parentheses, 1 minus sine of 18 degrees, I get 0.691, and so that is even less than baby G over 2. In our fourth problem, we're going to make it even more complicated by adding friction. I think you're ready for that, though. Welcome to our fourth and final installment in the boxes attached to ropes, attached to pulleys, and possibly dangling off things series. We'll do a little review before we begin of the previous problems and results that we've had so that we can make sense of what we learn in the end. In the first problem, we had a box. No pulleys, no ropes, no slopes. We found the acceleration of the box was downward at baby G. Not a big surprise. Our second one, we had one box and another identical box attached by a rope, and one was dangling over the edge. We found that the acceleration was half baby G. For our third problem, we made a slope of the ramp, and we found that our acceleration was even less than half baby G. We subtracted sine 18 degrees, which was about 31% or something. So it became an even smaller acceleration because one of the boxes was being pulled back because of gravity on it. In our final installment, we see that now there is also friction. There's kinetic friction right here. So let's assign some value for that kinetic friction. No, let's not even do that. Let's just assume that it is a number between 0 and 1, as all kinetic coefficients of friction should be. So let's look at this problem. We're going to have to look in the y direction on this box also. So let's pull that box out and do a free body diagram on it. I'm going to name this sucker box 1, and I'm going to name this guy box 2. We'll put a dot at the center. We'll say that the force of gravity must be acting downward on it. There must be a normal force so it doesn't go into the ramp. Okay, and there's the tension force this direction that is pulling the box because of the rope. And finally, there's a fourth force, and that force is friction. Before we can say the direction of friction, it could be this direction parallel to the surface, and it could be that direction parallel to the surface. So before we can talk about which way it is, we need to figure out which way this box will be moving. Let's assume it's starting from rest, so the direction of the acceleration is also the direction of the velocity. So if this starts from rest and is released, then this mass will be pulling down more than this mass is pulling to the left. And we can assume that the entire assembly is going this direction. And you can tell because I'm talking about the coefficient of friction for kinetic friction that there is motion. It's not just staying there. Now clearly, if this were Velcro or something, it would be possible for the static friction to be big enough to prevent this box from moving. But we don't have to worry about that in this case. It is actually moving because I've given you the kinetic friction coefficient. So we're going to say that friction acts this direction, and I'm going to label it F sub k. It's the force of kinetic friction. All right, are you ready? We need to establish a direction for x and y here. I think it makes a tremendous bit of sense to put x and y at the slope of the ramp again, so we'll only have to resolve one vector, and that is m times baby g. Put some dotted lines right here, follow along at home. This is the opposite side from this angle. This angle, of course, is also 18 degrees. This is m times g times so, or ka. So is the opposite, so this is m times g times sine of theta. This is m times g times cosine of theta, and we can apply Newton's second law in both directions. So let's say the net force in the x direction is mass times acceleration in the x direction. And we presume that will actually be the direction of the acceleration of the box. Let's see, we've got 3 forces in the x direction this time. So we're trying to find a sub x. We know that there is a force in the x direction that's positive, so that's the tension. And then we're going to subtract, just as we did before, m times g times sine of theta. And then I also have to subtract the force of kinetic friction. All right, pay attention, this is an x, that is a k. We can put this in a little box and come back to it later. Let's apply Newton's second law in the y direction also. Force times, let's see, net force is mass times acceleration in the y direction. And the acceleration in the y direction for this box, nothing. There are two forces in the y direction though. One of them is the normal force, and that's in the positive y direction, so I'll say F sub n, and then I have to subtract this force right here. Let me put some arrows on this so you can see that pointing into the ramp, and this is pointing down the ramp. So we've got the normal force minus m times g times the cosine of theta. Those are the two forces in the y direction. And this relationship right here can be very easily solved. So let's just do that. This says that the normal force is m times g times cosine of theta, a very common result. So let's put a green line over here and analyze the other box before we move on. The other box, of course, is extremely simple. It's got m times g down, and it's got tension up. Again, the tension is less than m times g, so that the box can accelerate downward. Because the box is accelerating downward, and we want the acceleration to be positive, so let's establish this direction as x, and then we can call that direction y. Our plan then is to take this, let's see, I'm going to take Newton's second law in the x direction, force in the x direction, mass times acceleration in the x direction, and this carries on because we're trying to find the acceleration in the x direction. And we've got m times g, which is positive, minus the tension force. Same thing we've been getting several times in a row. So let's, now we've got three equations, and oh man, how many unknowns do we have? Let's see, the acceleration in the x direction is not known. The tension is not known. The normal force is not known. And the force of kinetic friction is not known. So we've got three equations and four unknowns. That's undetermined. It's underdefined. So we need a new equation. Think of one. Have you thought of one yet? All right, I'll tell you. There's an equation that relates to these two suckers right here. And it says F sub k is equal to F sub n, times what? Mu? Yeah, mu sub k. There you go. A lot of people remember that as the definition of mu sub k, but you can also write it like this. In fact, I don't know why I wrote it like that. It's almost always written like this. There we go. So we'll take this equation right here and we'll use it to find out, well, let's just get rid of F sub k. So let's take this equation and rewrite it with our new information. Take this guy and bring it down here by using this equation into here. Then we'll have three equations and three unknowns, and then we'll be happy. T minus mg sine theta minus mu sub k times F sub n. See how I just really slickly plugged that in right there? Is mass times acceleration in the x direction. We're trying to get to the point where we only have acceleration in the x direction and a whole bunch of stuff we already know. Let's take this equation right here because it's so close. We could take this equation right here and substitute in for F sub n. Better put a lid on that one. You know what I mean. We'll have this new extremely long equation. T minus m times g times the sine of theta minus mu sub k times, and now instead of writing F sub n, I'm going to write mg cosine theta. And that's all still equal to mass times acceleration in the x direction. Our final step, of course, is to take this one equation that we haven't used yet, and what are we going to try to get rid of? T, right? Let's take this equation and solve it for t first. T equals mass times acceleration in the x direction. Let's write it as negative t is mass times acceleration in the x direction minus m times baby g, and then we can take the opposite, so we'll have minus there, and plus right there. So I'm going to take this definition of t, plug it in over here. Woo! And then we'll do a flurry of algebra and we'll be completely finished with the problem. Get ready. I've got negative mass times acceleration in the x direction plus m times baby g minus m times baby g times the sine of theta. Ooh, that looks very familiar to the previous problem. Minus mu sub k times m times g times cosine of theta is mass times acceleration in the x direction. Now this is not a pretty thing. You wouldn't really be happy to see that anywhere ever, but notice there's a mass in every term. Mass, 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 mass. Go on. Another thing that's bothering me is that the acceleration in the x direction, which is what we're trying to find, is actually on both sides. So I will add the acceleration in the x direction to both sides. Then we'll get two of them over here. 2 times acceleration in the x direction. Over here, we've got g minus g sine theta minus mu sub k times g cosine theta. Oh my goodness. Let's check our units. This will be fun, right? This has units of acceleration, meters per second squared. Baby g is also meters per second squared. Baby g meters per second squared times sine, which is unitless. Cool, that worked out. This is baby g meters per second squared times cosine, which is unitless, times mu sub k, which is unitless. So this is a reasonable answer because all the units agree. The next thing we want to do is factor out a baby g, and then we're going to divide both sides by 2. Check this out. This is actually really fun. We get baby g over 2 times 1 minus sine theta minus mu sub k cosine theta. Close parentheses, that is our acceleration in the x direction. Notice how it is even less than the previous answer because we're subtracting a positive number times the cosine of 18 degrees, which is also positive. So if you're interested in getting some numbers in here, we're going to plug in the sine of 18 degrees. Notice that last time what we had in the parentheses, we had g over 2 times some stuff in parentheses, and we evaluated that at 69.1%. So we're going to be even smaller here. We're going to say 1 minus sine of 18 degrees, and then we're going to further subtract mu sub k. Oh, what do you want mu sub k to be? Oh man, how slick is your box? I guess we'll call it 0.5, right? And then we'll multiply that by cosine of 18 degrees. Just to get a number, wow, we found it's only 21% of the acceleration that we had when we had the 2 boxes and no friction on flat land. So, it's the end.